Alright, here's the bar magnet lab. To begin, what is our mission here? It is to measure the B field produced by this bar magnet at certain distances away using an iPhone magnetometer, observing cool trends. Our models and principles here include magnetic dipoles, superposition principle, and distance dependence. What will happen is that the experimental results will closely align with the actual model's prediction, and we solve for n equals negative 2.889 and mu equals 2.815 amps times meter squared for the dipole moment of the magnet. Our ideas include the Biot-Savart law, which says that we can find the actual magnetic field at a point due to a point charge as follows here. And the B field of a dipole is really tricky to calculate because it's very complex with this formula here, with the dot product 2 in the middle. Distance dependence formula is shown above, which shows how B field falls off with the distance as shown here with a negative n that r is raised to times a certain constant k for the B field of a dipole here. And here's the linearized version as well for a logarithmic scaled graph that I can find later. For the experiment details, the system is the bar magnet, and everything else is in surroundings, including my phone itself, which is part of the surroundings too. And here's my scatter plot of the natural log of the B field at the x component as a function of the natural log of the r, or the radius, when this phone's axis was parallel to the actual magnetic dipole direction. I measured the above using an iOS app called Teslimeter with the phone, with my phone as the actual obs location as a long meter stick. Then I positioned the phone's magnetometer at a 45-degree angle from the bar magnet and found the off-axis B field to be 2.27 e negative 5 teslas. And here's the graph that I used for linearization. Here's how I found the actual dipole moment using my data as well as constants used in physics to solve for this equation where kr to the n power equals the following equation for a dipole's B field when parallel to the axis itself. So that's why I found this answer here. And quick quiz, which of the following statements describe what you observed? And the right answers are equal to 1 and 4 because when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, which makes sense because it decays as you get farther away from the actual magnet's location, because r, it's 1 over r for the function for the B field. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, which makes sense because the actual field gets bigger as you get closer to the actual location, because 1 over r shows that a smaller r value causes a bigger B field in general, so that's how that works. My code is here for dipole, which shows that I use the following moment of 2.815 am squared for the actual dipole moment, and here's my code for making the actual function as well as creating arrows for the dipole moments at different locations about the bar magnet, as well as places that are both, parallel to the axis, perpendicular, as well as orthogonal, or even at a slant axis away from the actual axes of the bar magnet. So here's the different calculations for that, and my code is very simplistic as shown below for the close script. And here's the actual thing I got for the output of the model, which shows the different arrows and their magnitudes and directions. For orange is parallel, blue is orthogonal, and purple is slant axis away from the bar magnet's location. And here my observed B value, or B net, equals 2.27 e negative 5, whereas the predicted value for the model is equal to 2.837 e negative 5, which shows a very small percent error of 19.9%. So it's pretty accurate in general for the model compared to the actual, observed location and B field for the observed axis. I assume that the bar magnet acted as an ideal dipole, but this could be very far from the truth. And other devices like, of course, laptops, AirPods, and also phones would mess up the magnetometer measurements quite a bit from what I would like it to be. The location of the actual magnetometer is assumed instead of actually found precisely, as well as we assumed that the distance dependence formula was actually held for this magnet. And what if I actually hadn't aligned this with the North Pole, but instead lined it a bit askew? That would cause the field from the Earth to interfere with the actual measurement for the bar magnet's B field and skew our data quite a bit. And what if two identical back-to-back bar magnets were used instead to cause the B field? In that case, we have a doubled magnitude of the actual B field, but we have the same direction for that B field because it's just two magnets with a double Q, but also the same direction because they're both in the same alignment and have the same dipole moment at that axis. To conclude, modeling bar magnets as ideal dipoles for calculations for B field can be pretty accurate in general and get the job done, as they follow the distance dependence formula in general and are pretty accurate in that sense. Geographical north can be very different than the actual true magnetic north because your phone's compass is used to find the geographical, not the actual magnetic north pole, so it's very different than what you're taught in this class for the magnetic North Pole, for where all the Earth's dipoles, protons, or whatever, positive charges are concentrated. And when doing off-axis double pivot calculations, the models really help simplify calculations a lot and doing wacky dot product math and help you with the very difficult math that is involved in doing those, B field calculations for off-axis dipole moments in E fields. So it's very helpful to use these models to amplify your calculations for that.